So now today we will discuss Lagrangian equation of motion. So in order to discuss Lagrangian, so we will discuss both the case of classical mechanics. So we will discuss both classical mechanics and classical field theory. They are very similar, so we will discuss them parallelly. Okay, so let's start with the simplest case, which is the case of classical mechanics. So let's say then in classical mechanics we are given with an action S which takes the following form. Okay, so let's say for the moment let's not specify what is the range of value of t. Let's just denote it as m. Then from Euler's principle, any classical configuration should extremize the action. Okay. So this is often known as this calculus of variation. So the way we do it is that let's say phi c is the classical configuration, and let's say we denote just take a small change of that. Okay, and we ask how does the action vary? So let's check it. So let's say delta S will be delta L phi dot, where delta L is the change of the Lagrangian, due to variation. So how do we do that? So let's say Lagrangian is just a function of phi and phi dot, which means that we take the derivative of the Lagrangian, functional derivative of the Lagrangian with respect to phi. Sorry, this was not correct. So we take the functional derivative of the Lagrangian with respect to phi, and then we consider the variation of phi which is delta phi, and similarly we take the variation of we take the derivative of the Lagrangian with respect to phi dot, and then we consider the change of phi dot. Okay. Now delta phi dot is simply ddt of delta phi. Okay, then this term I can write as ddt of delta L delta phi derivative of L with respect to phi delta phi plus not plus minus d dt of del L del phi delta phi, right? So this term can be written in this following way. So if I put it back, if I put this thing back there, then I get delta phi dt minus d dt of del L del phi dot times delta phi plus dt ddt of del L del phi delta phi. Okay. So you see now for this term, I can use Stokes' theorem. So and this term gets contribution from, so this term, let's say this term is then just simply becomes delta m del L del phi delta phi. So then this term gets contribution from the full range of integrals. This term gets contribution from the full range of integrals, whereas this term gets contribution only from the boundary. Okay. So then this fact, this is usually written as that the equation of motion, so that then the action is extremum, xn is extremum, or in other words, for the classical configuration must satisfy this term equals to 0, but delta phi is not equal to 0, which means that this term satisfies del L del phi minus d dt of del L del phi dot equals to 0. Okay, subjected to boundary condition that del L del phi dot delta phi at boundary must be 0. Okay, this is one very important thing to know, that we get only equation of motion subjected to a boundary condition. We do not get equation of motion which are just independent of boundary condition, unless, so there is no boundary conditions. Only if delta m is 0. Okay, so let's consider an example. This is too abstract. Let's consider a simple example. Let's consider del L equals to just half m phi dot square. Okay. So in this case, then equation 1, oh, this is phi dot. Yeah. Then equation, in this case, the equation 1 from 1 we get d dt of m phi dot equal to 0, which is same as m phi double dot equals to 0, subjected to, so let's say my action was, in this case, let's say the action was we are going from time a to b dt L, subjected to delta L delta phi dot delta phi, sorry, del L del phi dot delta phi, which is same as m phi dot delta phi at boundary, so which is same as m phi dot at t equals to b delta phi at t equals to b minus phi dot at t equals to a delta phi at t equals to a. Okay, so this term gives us boundary condition. So then you should always remember that when we are taking, when we are doing this partial derivatives, when we are doing this equation of motions from Euler-Lagrange equation, this is called Euler-Lagrange equation, this one. This always comes with a boundary condition, okay, and unless you satisfy the boundary condition, this extremization principle is not correct. Okay, often we just focus on the equation of motion without focusing on the boundary condition, but the same extremization principle gives you the all possible choices of boundary conditions, at the same time it also gives you the equation of motion. Okay. Now we can do classical fields. Okay, so for classical fields we have to now just generalize this, so where it was, so we have to just generalize this to now multivariables. So this will be generalized to some ddx, when x takes again over some range m, and now L depends on phi and phi mu, where phi mu is just derivative with respect to phi. Okay, so let's write it again. So we are now doing classical fields. So in this case, the Lagrangian just depends on phi and phi mu, where phi mu is del mu of phi, and the action is ddx, which takes value over some range m L. Okay, now we do the same thing. Now we want to find the classical equation of motion. So this is for, we are trying to find the classical equation of motion for classical fields. So how do we do that? We again do the same strategy. So let's say the phi goes to some phi plus delta phi, and we want to know how the action changes. Okay, so then the way the action changes, delta S is simply this plus derivative of the Lagrangian density with respect to phi, delta phi. So this is the Lagrangian density. Plus derivative of the Lagrangian density with respect to phi comma mu, which is basically the derivative of the phi with respect to del x mu times delta phi mu. Okay. Now again, delta phi mu is just derivative of the delta phi with respect to del mu. Okay. Then we do the same strategy. We write this term as del mu delta L, del derivative of the Lagrangian density with respect to phi mu delta phi minus delta mu derivative of the Lagrangian density with respect to phi mu and then delta phi. Okay, so this term just becomes this. So if we put it back in this expression, we get like derivative of the Lagrangian density with respect to phi minus del mu derivative of the Lagrangian density with respect to phi mu delta phi plus ddx mu del mu of I'm recording lectures. I come. Okay. So del x mu delta phi. Okay. Again, for this term, we can use Stokes theorem. Stokes theorem. And this term then can be written as, so there was an integration over m. So the second term, only the second term, so I do not say equality. The second term then can be written just as n mu delta L delta phi mu. So these mu's are contracted times delta phi. So again, like the previous time, you see there are two terms now. there are two terms. So there are two terms. Usually this term is called bulk term, and this term is called the boundary term. Okay. And again the philosophy is the same. The equation of motion comes from the bulk term. And the boundary condition come from the boundary term. So then the equation of motion in this case, is simply this one, which says that del phi is equal to del mu del phi mu. Okay, subjected to n mu del L del phi mu delta phi restricted to the boundary must be 0. Okay. So then again in this case, when you try to derive the equation of motion for a field, you have to satisfy this condition. So when you try to derive the equation of motion for field, you have to satisfy this condition, because this condition gives you the boundary condition. And I keep stressing on this because often very rich physics is encoded in this case. Often the very rich physics is encoded into the boundary term, and unless you set the boundary term equal to 0, the problem of the extremization principle is not correct, right? Extremization principle gives both the equation of motion. So let's write extremization principle gives both equation of motion and possible set of allowed boundary condition. Actually I was too quick here. You see the boundary condition only requires that this dd minus 1x delta m is equal to 0. As long as this is satisfied, this is good. So one can imagine non-local boundary conditions. Such that even if the integrand is not 0, but the integral is 0. So this is allowed. Nobody says that you have to choose a local boundary condition so that the integrand has to vanish. As long as the integral vanishes, an integrand may not vanish, it is still fine. But often for physics we impose even more stricter condition which say that local boundary condition. Local boundary condition. And local boundary condition demands that the integrand vanishes everywhere on the boundary. Okay, so you see that this is a stricter condition. So local boundary condition is stricter condition. Local boundary condition is not necessary. Is not necessary. But it is convenient. Okay, so with this thing you should always do the problem of calculus of variation, and you must always remember that the extremization principle gives both the equation of motion and possible set of allowed boundary conditions. Okay, so in the next lecture we'll come back and we will discuss the case when we have a symmetry in the Lagrangian formalism. What is the consequence of that?